Welcome back to Episode 7 of our 12-part explainer series on U.S. Patent Number 12664-142. Today we are uncovering what is essentially the ultimate cheat code for protecting complex software innovations. If you've been following along with us, you know we've really dug into the structural mechanics of the Hierarchical Script-Database. But right now, we're going to bridge the gap between that architecture and the law. So here's the massive challenge facing software engineers and IP attorneys today. How exactly do you prove to the patent office that your code is a concrete machine and not just, some mental process? Historically, the courts have really struggled to understand software. Think about it. It's invisible, it runs on generic hardware, making it incredibly easy for a patent examiner to look at your brilliant architecture and just dismiss it as merely a mathematical algorithm or an abstract idea. Frustrating, right? To tackle this, here is our agenda for today's explainer. First, the Alice Step 2 trap. Second, the Step 1 bypass. Third, Addis's hardware blueprint. Fourth, HSDB, merging noun and verb. Fifth, code-data locality in action. And finally, the future of software IP.
All right, let's jump straight into Section 1, the Alice Step 2 trap.
Our journey starts with a legal boss fight that has literally ruined countless software patents over the last decade. I'm talking about the infamous 2014 Supreme Court Alice decision. If you're building software, this is the shadow hanging over your entire IP strategy. The Alice framework demands we ask 2 consecutive questions to figure out if your software is actually eligible for a patent. Step 1 asks, is the claim directed to an ineligible abstract idea? If the answer is yes, boom, you are forced into Step 2, which asks, does it have an inventive concept that makes it significantly more than just that abstract idea? And this brilliantly illustrates the trap. If you get caught trying to prove an inventive concept in Step 2, you're in serious trouble. You're basically stuck arguing that your routine generic computer components are somehow doing something magical.
Now, why does this matter to you? Because if you are forced to fight your battle at Step 2, the Patent Trial and Appeal Board affirms eligibility rejections a staggering 90% of the time. Let that sink in for a second. A 90% failure rate. It means that unless you can fundamentally change how the examiner views your invention right out of the gate, your software is effectively unpatentable.
Which brings us to Section 2, the Step 1 bypass.
So to win this boss fight, you absolutely have to use a cheat code. You bypass Step 2 entirely by proving physical technological improvement right there at Step 1. You got to convince the patent office that your software is inherently a structural improvement to the computer itself. Let's look at 2 cases that perfectly define this technical functional boundary. First, custom media. Here, the inventors partitioned a local hard drive specifically for targeted advertising. The court looked at that and said, no, that's just an abstract commercial idea utilizing a generic hard drive. So they failed. But then, look at Unilock. These inventors appended an additional data field to Bluetooth messages to physically reduce network latency. The court said, yes, that is an eligible technical improvement to the network itself. Unilock survived at Step 1. The takeaway here? If you just organize data for commercial purposes, you lose. The courts playfully pointed this out in the IBM v. Zillow case regarding a digital mapping interface. They basically said, if you just automate something cartographers traditionally did by hand using translucent paper, you've essentially just invented a very expensive pencil. It's a quintessential do-it-on-a-computer patent, and the courts will throw it out every single time. You absolutely must show a structural enhancement.
Moving right along to Section 3, Addis's hardware blueprint.
Let's look at a major success story from 2022 that gives us the exact blueprint for protecting data architecture, and it perfectly sets the stage for our analysis of U.S. Patent Number 12664-142. In the ADESA versus Avery Dennison case, the court analyzed an RFID transponder chip that featured a specially encoded serial number space. They didn't see an abstract mental process here. No, the court explicitly ruled that this was a hardware-based data structure. By designating a specific field of bits, the inventors established a patent-eligible physical logical alignment that literally eliminated network latency during manufacturing. It physically improved how the data was encoded. Huge win.
And that brings us to our primary weapon for defeating Section 101 rejections, code-data locality. This is the concept of keeping executable instructions and the data they manipulate physically close to each other in a system's memory. When you do this, you reduce the distance data must travel across the system bus. You decrease power consumption. You accelerate instruction execution. You are fundamentally altering the physical and logical behavior of the computer itself, exactly like Addis did.
All right, Section 4, HSDB, merging noun and verb.
Now we can finally look at how the Hierarchical Script-Database, or HSDB, executes this legal blueprint to perfection. It takes the concept of code data locality and bakes it right into the very foundational architecture of the database. If we look at this historical evolution, we see a fascinating journey. Back in 1966, systems like MUMPS tightly integrated the language and the database. But over time, the industry decoupled them. That led to modern NoSQL and serverless systems where the compute layer and the data layer are just completely separate. This forces a massive object relational impedance mismatch, requiring really heavy translation drivers. Well, the HSDB resolves this friction by pursuing total architectural coupling. It asserts that the program and the data are structurally isomorphic. Essentially, they are the exact same thing.
Think about it linguistically for a second. Traditional systems separate nouns, the data objects, and verbs, the instructions. The HSDB, it places them right next to each other in cohesive sentences. By utilizing JavaScript as a single, homogeneous language for both data retrieval and scripting instructions, the HSDB actually merges the application layer and the database layer into a self-evolving runtime kernel. By embedding executable logic directly inside the database nodes, the HSDB eliminates the need for distant network translation layers. It is a straight-up eligible hardware-level enhancement, completely echoing the success of that Ada Sasa RFID chip. Let's dig deeper in Section 5, Code Data Locality in Action.
Now, it's one thing to just say you're merging code and data. It's another thing entirely to mathematically enforce it so a patent examiner cannot deny its structural reality. At its core, the HSDB utilizes a mathematical framework referred to as Pythagorean metal. It models data and execution not as some static state machine, but as a non-halting, self-reproducing automaton. It uses the scale symmetry-based exponent of c minus b over a to the power of n to produce totally unique geometric coordinates for data structures. Because the code execution path and the database retrieval path follow the exact same recursive mathematical coordinate system, the database state space is physically bound to the logic. It's locked in.
Let's look at the actual patent claims to see this in action. A parent script defines the functions of a parent vertex in a tree structure. That script contains executable instructions to instantiate a child vertex, generate a child script, and seamlessly form a link connecting them. So instead of an application querying a distant passive database server, these event handler vertices literally construct and link executable scripts right within the data tree itself. It is a localized, self-modifying growth process that absolutely maximizes our cheat code of code data locality. Which brings us to our final section, Section 6, the future of software IP. So, what should you take away from this intricate dance of law, mathematics, and architecture? How does this redefine the future of software intellectual property? Well, the rules of the game have been clearly established. First, you must avoid generic do-it-on-a-computer claims at all costs. Second, the courts have been exceptionally clear on this. Improving a user experience, or UX, is never enough on its own. Instead, you've got to focus on specific improvements in computer capabilities, reducing latency, saving memory bandwidth, eliminating translation layers. Just like the precedents in Infish, visual memory, and ADASA, if you integrate instructions directly into the hardware's data structures, if you can claim that physical code data locality as a concrete structural improvement, you own the innovation. You bypass Step 2 entirely, and you secure the patent. As we close out Episode 7 of this explainer, I really want to leave you with this thought. Look at your own architecture. When the patent examiner eventually looks at your life's work, will your next software build be dismissed as an abstract idea, or will it mathematically and structurally prove itself to be a concrete machine? Ask yourself how you are architecting your next project, and we'll see you right back here in Episode 8 for the next piece of this fascinating technological puzzle.